All right, afternoon, everybody. Thanks for joining at a different time than we normally do. Because Tim is based in the UK, we didn't want to force him to stay up late on a Friday. So he's going to be here talking about a topic that I know a lot of us have chased down for probably decades at this point. And if the emails that I've received from some of you are in any indication, you're still chasing these problems down. So I'll turn it over to Tim and the team to talk a little bit about jumbo frames, and hopefully we'll have a little bit of discussion at the end, because I know that we have some friends and colleagues from the community that don't always come to these calls, and they were interested in hopefully talking a little bit later on. So I'll turn it over to you, Tim.
Great, thanks very much, Jason, and thank you for having me. And sorry, I'm messing around with your times and time zones. So I've renamed this a brunch and learn seminar rather than lunch and learn. I understand you might be anywhere from having breakfast now to having lunch anyway. So it's good to be here. So I'm Tim Chown from JISC. I'm Network Development Manager there. I know quite a few of the ESNet people from over the years. I think my colleague Chris Walker is on the call, and Raoul might be, but I can't see easily right now. So hopefully they'll join the discussion, but they've contributed to this deck for me. So today's agenda, I've got maybe 15 to 20 slides here just to sort of set the scene and put some of the issues before you, and hopefully we can have some good discussion. I don't know whether you normally take questions as you go or at the end, but whatever's normal, I'm ready. So I'll start with some introduction about JISC and Janet, just for those of you who might not know what that is, and then get into the jumbo stuff. So JISC is the organization that I work for. We manage and operate Janet, which is the UK's NREN, or the UK's network that connects universities, colleges, etc. We support V6 natively for 20 years. We've supported jumbo frames on the network for many years. And our network is obviously a little bit smaller than many in the US, but we have 8 main core points of presence. The sort of black part of the network there, running at 800 gig in the south up to about 200 gig in the north. It's more in the south because that's where most of our external connectivity and peerings are, and so most of the traffic is going in and out there. About 9,000 kilometers of fiber and about 1,000 sites that we connect there. We have external connectivity to most of the places you'd expect, and probably that most of your networks do. From the R&E point of view, of course, the Chown link is the important one. We're currently 300 gig onto Chown, and that's starting to look a little bit warm, so that might be being upgraded soon. But we have direct connectivity to a whole load of other things, probably totaling about 5 terabits of capacity now. A couple of other things I'll just mention with the sort of JISC Janet context, in case they're of interest to you. One is the research network engineering community that we started last year. A lot of this has been inspired, obviously, by what ESNet's done with Science DMZ, many discussions with people like Eli, who've been exceptionally helpful for us. In fact, Eli has guested in one of the talks we've had in this series for us, which is much appreciated. So we have some discussion on a mail list that you're welcome to join at the foot there, and we have a monthly get together, a bit like this call, where someone will talk about something, maybe a project they're doing, how they're moving the data around, how they're engineering things on their campus, and we'll sort of chat about topics. So yeah, you're welcome to join that in the list, but obviously it's 2 p.m. UK time, so maybe not so ideal for many of you. The other one that you might find useful are some various network test tools we have for performance testing. There's a web page there that sort of describes them and the endpoints you can test against. The usual suspects, IPv4, 3, Ether, perf sonar, various DTN tools like Globus, etc. We can add more things on request. If you think, looking that there's things we might or should be adding that maybe ESNet run to help your sites test, then I'd be interested to hear from you. We have 2 test facilities, one's 10 gig connected and one 100. They're all dual stack or configured with 9,000 MTU. So yeah, if you want to do some testing, I'm very happy to talk, but a lot of it's open, you can just use it. So on to jumbo frames. So why the interest? I mean, intuitively, as you get higher link capacities, the 1500 bytes becomes an increasingly diminishing percentage of that capacity, if you like. So larger frames intuitively make sense to reduce the amount of overhead on a sort of per packet basis. There has been interest over the years, sort of like waves on the beach coming and going from different communities to make use of jumbo frames. In the discussion leading up to this, where Jason threw out the discussion a little wider, Matt sent a link of a pointer to an archive of his former site, and there's a lot of good stuff on there from a few years ago. You're probably mostly familiar with the WLCG, the Worldwide Large Hadron Collider Computing Grid, quite a mouthful. Obviously, that's an infrastructure that spans several hundred sites around the world that are working on the major CERN experiments, distributing data, computing, recycling results, etc. They made a proposal in 2018 to be using jumbo frames widely across the infrastructure. That was Sean McKee and others that proposed that. But as yet, despite that, there's no widespread or formal adoption, which is surprising, perhaps. And other projects have also recommended the use of jumbo frames, but again, maybe adoption isn't as wide as you might hope. The experimental evidence, of course, or I say of course, the experimental evidence that we've seen, and I'll show you some examples of just snippets of that later in the talk, backs up the maths that the larger MTU size does improve performance. The flip side of that, though, is that there are operator concerns. We do come across sites where they've tried implementing 9000 MTU and then run into some issues, and people are a bit nervous. Obviously, networks are now so critical that any change has to be given due consideration, and if there are problems and concerns, those will make people nervous. But I think, or I'd hope, and maybe most of the people in the call here would like to see more use being made of jumbo frames. So hopefully we can have a good discussion and see what we can do towards that. You should understand what we mean by a jumbo frame. Maybe this is kind of commonly understood by all of us and everyone on the call. The definition that you will generally see is the jumbo frame is an Ethernet frame with an IP payload bigger than 1500 bytes. The goal from the what we saw with the WLCG spec was that the end sites should be able to set their MTU 9000 within their LANs and have those packets traverse the intervening networks without fragmentation. And there was sort of an implicit choice of 9000 for that for hosts as the sort of jumbo frame size. But you do also need to bear in mind that even though that's what you're using on the local network, the intervening networks may be using technologies that add some overhead to that. So you need to think about that as well, whether that's within the campus or on the NREN backbone. The WLCG recommendation of 2018 said a few things. There's a link to it there if you want to go and have a look at it. That the network path should allow the MTU size up to 9000, but also stated other things that are kind of required to make it work, like not blocking path MTU discovery packets, as per the RFCs listed there, and suggested an actual frame size of 9080 to be supported by all network devices on the path to allow for the overhead. Another example of a project that's been recommending the use of jumbo frames, and I've included it because it's an example of a project that's going to be moving a lot of data around, the square kilometer array. You may be familiar with that. It's in development now. Data is going to need to be shipped at least 100 gigabits a second from South Africa and Australia to various parts around the world. I'm sure it will be coming to the States. It'll be coming to some a big data center in the UK as well at RAL. And their precursor project called IANAS, where they've been testing various data transfer methods and network technologies. There's a report there that's a very interesting read for other aspects beyond just the jumbo frame size of it. They're recommending the use of jumbo frames as well. How jumbo is a jumbo frame? Well, I've been saying 9000 MTU. I mean, that's not the only option to have a frame, obviously bigger than 1500. There's a lot of options there. Looking back, my colleague Chris Walker, I think, is on the call, found a 20-year-old document. Maybe some people on the call were involved with this. Maybe you can tell us about that in the discussion. There's a link there to some of the rationale as to how we ended up with the 9000 MTU as a sort of, I wouldn't say default, but the sort of currently widely used MTU for jumbo. I found it quite amusing. There were some really good technical things in there. The last reason was, and 9000 is an easy number to remember. Now you might say, well, isn't 8192? I just thought that was amusing. The interesting question, though, is that how widely supported is this MTU size within the NRENs, within Internet 2, ESNet, and so on? I don't know. Within Europe, I'm also not sure. I've said that Janet supports it to an extent. Some other NRENs we speak to and talk to do, but there are clearly some that don't. So having some data on who supports it would be very interesting. I'm not sure that's widely known at the moment. The status on Janet, if one of our connected sites has a standard IP connection to Janet and they use 9000 MT on the lands, that will just work. We have enough overhead for that. The corner case is where we're doing layer 2 VPNs with what we call our NetPath service. That may not work. We need to do some further investigation of that. That's configured that way for historical reasons. That we'll need to look at, but for the default case, for our default connection type, jumbo frames will work. However, having said that, we had our NOC look on the background to see how many jumbo packets are seen, and there's only 2 sites on Janet that we have clear evidence of them using it. One is RAL, and the other is Queen Mary University, sorry, in London. We kind of hoped to see more people making use of it, but for some reason they don't. Another thing to bear in mind, instead of all our infrastructure is dual stack, I'm sure all of ESNet is, and Internet 2, etc. There are differences, of course, in the way fragmentation works for v4 and v6. v4 allows it anywhere along a path, so the traffic, say a 9000 MTU packet may get to a router on path, and that router may fragment into 1500, and then it's up to the receiving host to reassemble. Either of those actions can cause performance issues that people can rightfully get concerned about, or potentially, a firewall at the far site might see all these fragments arriving towards a destination and just drop them. And we've seen examples of that happening. One of the nice things to note, and it's on the wonderful faster data site that ESNet maintains, there's a nice Linux option to do v4 MTU probing that the site recommends you set by default as when you're doing all your tuning and so on. So that's something to bear in mind. That exists for v4 at least, if not v6. The problem with v6, or the difference with v6, I should say, is that you can't fragment on path. So you need to know the MTU for the sender, and the sender must send it the correct MTU for the link. So you need to do the PMTU discovery in advance. And the major thing with that is that if there's a link on the path that won't take 9000, if that's what you're trying to use, you do need to get the packet too big message back so that the sender can adjust. So it's important that sites don't blindly filter ICMPv6 as defined in the quite old now RFC 4890. And we have come across examples on Janet, particularly Queen Mary, who I mentioned as one of the sites that I use in jumbo frames. When they initially started, their campus firewall was dropping all ICMPv6, which caused obviously problems for them. But that's now resolved, but you do see this happening. The potential benefits, fewer packets in theory, means that you're processing fewer packets, which means there's less load on the CPU. We note that link capacities are rising. There's increased use of 400 gig interfaces now, whereas CPU speeds may be rising less. Certainly larger frames allow you to get faster ramp up and recovery for traditional TCP algorithms that back off in the event of packet loss being an indication of congestion. If you look at the TCP calculator that Switch kindly made available, which is quite a nice little resource, you can see if you put in the bigger MSS, the Mathis theory, you're getting significantly more throughput for using a higher MTU. But as I say at the bottom here, experimental evidence is always good to see. So I've got 4 or 5 slides now of just some anecdotal evidence from various tests that we've done with my colleague Raoul, who I'm not sure if he's on the call. He may or may not be, sorry, I don't know. He did some tests earlier this year, or maybe this one is even late last year. This was from a Persona server in the Dutch NREN to one in the Brazilian NREN RNP, so that's about 100 millisecond round trip time. One of the nice things there, as an aside, is that Surf were prototyping a streaming telemetry platform. So rather than just having the sort of 5-minute traditional SNMP-like averages of utilization, we're seeing the exact throughput on almost a per second basis in these plots, which is very interesting, as you can sort of see some of the ramp up, ramp down activities of the protocols there. But the long and short of it is that with IPv3, for example, getting 31 gigs with 9,000 MTU versus 20 gig with 1,500. So that was 50% more throughput for 9,000 MTU. There's a link there to the document where Raoul's documented more of the testing. There was another one Raoul did where he ran from our server in London to one in the States on the WLCG sites. This is, I thought, quite a nice use of perf sonar by Raoul. What he did was, this is a link that I think is monitored as just one of the WLCG links on one of the meshes. So it's doing the perf sonar throughput tests typically 4 times a day, every 6 hours by default. And what he did was change the MTU down from 9,000 to 1,500. And then you can see on the plot there, about halfway along, the throughput dropping because the perf sonar results drop because the MTU is being changed. And that's about 14 gig down to 6 gig of throughput. That's just a single stream iPerf test, which is quite, 14 gig is quite respectable for a single stream iPerf, I think, on perf sonar. The other really interesting thing there, which I asked him about because I wasn't quite sure what he did, that the dotted line that dips later there, he made another change, which was to change the London, our perf sonar node, to the default OS tuning. We generally follow the faster data advice and maybe tweak it a little bit. But that shows you that the drop in throughput you get if you don't tune the system, which I thought was another quite nice way that perf sonar is showing that in a nice visual way. Another test Raoul did was from or between the Dutch NREN and our server. So this gets you more of the sort of advantage you or hope to see. So you're seeing here 23 gig with 9,000 MTU and 6 gig with 1,500, and also no retransmits with the larger MTU, which is interesting, where there's considerably more with the 1,500 MTU. So we need to do some more tests and see what sort of correlation is there with MTU size and retransmits. Those are 3 things Raoul did that he kindly sent me to include. Richard Hughes-Jones gave a talk at one of our RNE calls, so I've borrowed a couple of his slides as further examples. So he did 2 sets of tests. He's the chap, if you remember on the previous slide, he's involved with the SKA project pre-testing, very experienced chap who works for Chown. So he did these tests here, which were between London and Cambridge, so a very short round trip time of 3 milliseconds. So 2 sites very close together in the UK. He was there getting 37 gig with 9,000 MTU and 15.8 with 1,500. And the interesting thing there is if you see the little red 98 down the sort of bottom middle there, that's showing with the smaller frame size, the CPU is getting hammered more by the fact there are simply more packets. So this is a nice example of where the CPU in the top one is only 87% at 9,000 bytes. So it's showing that advantage. And then the other one he did was London to Australia. Chown have done some other tests probably 3 or 4 years ago as well now to Australia, showing the difference in throughput between the RNE networks and the commercial networks, which is a very interesting piece of work they did. It showed how bad it is going over the commercial networks versus RNE. In this case, this was for his jumbo frame tests, and you're seeing here a much more significant difference of 21 gig for 9,000, 3.4 for 1,500. So those were just some, they're not exactly hugely scientific, and I think they're good examples of the performance increase, different levels of increase depending on the scenario. There's a summary of them here in this slide. Chris kindly pulled that together for me. So you can see the differences there. So there's clear advantage. So that's the advantage potentially, but what are the downsides? Are there downsides? That's something we can obviously discuss. And you have discussions with people at sites that have concerns. They're generally aware that the router and all hosts on our land should run the same MTU. You can sometimes get away with a mixed mode case, but it's generally advised to keep the same MTU for anything in the same broadcast domain. And it should be possible to put the non-jumbo hosts in a different network. Whether jumbo frames are appropriate for all networks, that's another good discussion. It might be appropriate for a Science DMZ, for example, where the systems are doing large-scale data transfers, but for a Wi-Fi or just some administrative desktop LAN, maybe not needed. The one we do see and hear more comments and complaints about is the PMTUD not working, in particular, of course, for V6. That's something of a concern. And if you just have things not working for one site that you speak to, that can cause significant problems, even if it's working for all the other sites you speak to. So it may be that a number of sites in ESNet are running 9,000. The question is, how are they interfacing and working with the sites that aren't running 9,000? Because the filtering and the packet dropping could be done at the far end. There's the question as to whether the NREN backgrounds have enough overhead in the MTUs they support to actually do this. It would be interesting maybe to do some testing to try and figure out that and whether it's the case, and how often fragmented V4 packets might be dropped. We've seen examples of people raising this in meetings in the UK. In one of the HPC SIG meetings we had, there were people citing examples of this, and maybe there's other concerns as well. Maybe we can discuss that very shortly. I think I've only got 1 or 2 more slides left. Oh no, I've got this persona example. So one of the cases that may intuitively cause people to be concerned who are doubtful about doing jumbo frames is, well, if I go to 9,000 and most of the people I'm speaking to are still 1,500, is everything going to be okay? And from the the examples and the testing we're doing, it seems to work well. We've used Perf as another way of looking at this and seeing where it works and doesn't work. We have a mesh in the UK for all the UK sites that take part in the WLCG. That community is called GridPP in the UK. There's about 20 universities that take part. And through that mesh, we can see the MTUs that people are using, at least on their Perf systems. And we kind of make a jump from that to assume they're using similar MTUs on the systems that are transferring data. That may or may not be true, of course. So, I mean, here's an example of, for that mesh, looking at one of our JISC reference Perf servers that's running 9,000 to the University of Bristol, where they're running 1,500. Here's an example of where you can, through the toolkit page of Perf, if you just hit the details button without logging into the toolkit page. So generally, most systems have this open. You can just look and see what the different interface MTUs are. So you can see here that although the main throughput interface there has 9,000 MTU at least. And then looking at the Perf plot for between our server in London and Bristol, over time you can see it's up and it's down, and there's generally better performance from our server into Bristol rather than the other way. But whether the other way is due to the lower MTU or it's just more likely that there's more real actual traffic that the test traffic's containing with, we'd need further investigation for that. But there's nothing badly or seriously wrong there with 9,000 to 1,500 into working. So it's nice to be able to show examples to people of that working. So I think that's everything I have to say. I did say to Jason, I'll try and keep it to about 20 minutes of talking so we can have plenty of time for discussion. What sort of things might we do as a community that we do between different NRENs and RNE networks? Certainly running more performance tests would be no bad thing. Richard Hughes-Jones, who I've mentioned a couple of times, would like to run more sort of SCA-oriented, SKA-oriented tests between Australia and South Africa and the UK, but possibly you could do that to the US and ESNet, for example. It would be good to take a fresh look at evidence of use on different NREN backgrounds. As I said, at JISC, we've looked at the Janet traffic and only seen any significant use of jumbo frames by a couple of sites, which is disappointing when we have 160 universities and 10 or 12 really major research sites connected to us. It would be useful to explore support for the larger MTUs across the network. Maybe we could use tracepath for that. Maybe we can do some things with Perf and establish where it should be working, or any networks where it won't work, and then have some conversations there. And I think a nice thing to do would be to document best practices for getting jumbo frames more widely deployed. Maybe we can do something there. There's something about, it could be something that can be added to the faster data site, for example. I know there's already some things there, but something that we can distribute and point people at. So final slide, who on the call is already running jumbo frames? Has it been a happy story? Do you have specific concerns or maybe some past war stories? It was interesting in a previous discussion we had in the UK with RAL, the big site at Harwell that hosts the WLCG tier 1 for the UK. They've got 200 gig resilient onto Janet and another 100 gig optical to CERN. They turned on 9000 MTU a while ago. They had a very bad experience. They immediately turned it off again. But credit to them, they learnt from that. And then a few months later, they turned it back on and now they're running it. They're very happy with it and they're not seeing problems. So that's a good news story. As I say, we could do more tests for support of 9000 MTU. We could think about what sort of things to advocate in best practice documents. Maybe make it clearer that jumbo frames could be a default part of a Science DMZ deployment. And with as some people on the call may know, I do go on about IPv6 quite a lot, but yeah, jumbo frames and IPv6 should just be in all Science DMZs, I think. So that's it. I think that's all I have to say. There's some contact information there if you want to get in touch, but maybe now I can stop sharing and we can have some discussion. I think my first question is, how widely is 9000 for you? Is how widely is 9000 MTU or a jumbo frames used in ESNet? And is it been a happy story if it is widely deployed? So I shall stop sharing there and hand back to Jason maybe to share some discussion.
All right. Well, I mean, we have a lot of people from various campus networks, regional networks, backbone networks that are represented here on the call today.
Okay.
So everybody does have the ability to sort of unmute themselves as they see fit, or use the hand feature, and I can sort of be the moderator. You know, the immediate question, and you know, not to put my colleagues on the spot, but I do love doing that, is that we have Dale and Mike and Joe Metzger all here, and Jay, a couple of others as well. So if somebody wants to maybe just give a little bit of background on ESNet, that may be a good starting point, and then we can have some others from the regionals and campuses speak in as well.
Hey, Jason. Can you adjust the Zoom so we can actually share video? I think that's like disabled for non-presenters.
Yep. I'm sorry. There you go. This is why Jason doesn't know how technology works. Go ahead.
Yeah, I think like I even combed my hair. Come on.
Hi, Dan.
Hey, Tim.
We've been exchanging some emails about WLCG packet marking in the last few weeks for an internet draft, which has been good fun.
Yeah, I thought I would first share a link to documentation I wrote on this topic 14 years ago at my previous job, and really had not seriously considered it since then. But at the time we were doing testing on the enterprise network, we did come up with a list of rules that we had, you know, sort of identified as like actionable for a LAN administrator to follow. One clarifies one of your points, Tim, like all hosts on a given broadcast domain should be configured to use the same frame size, as there is inherently no packet too big message at the Ethernet layer, right? That's an IP layer construct. So we were concerned about that. It was particularly relevant, I think, for storage backends like say NFS using UDP, things like that, where you wouldn't necessarily have like an MSS style negotiation happening.
Yeah.
So that was like an easy rule, right? So the next rule was all routers, obviously on that VLAN, also must be configured to use the same frame size. Again, we're trying to be prescriptive. You can tell the point in time this was written is that all hosts must be gigabit Ethernet or better, as I think that's when jumbo frames were formalized in the IEEE spec. So for fast Ethernet and slower, it was not an option, if I recall correctly. And then we have all sort of the same sort of things on ICMP filtering and that sort of stuff.
So there's some theory there, Dale. Did you get it deployed and was it successful?
I see some of my former colleagues on this call asking if it's still running, but from what I remember, it was only deployed so the backbone, of course, for the enterprise network was 9K plus clean at the time. but there was maybe only one science DMZ-esque LAN that had it in production, which was certainly appropriate for the typical use cases. Now, I would say where my thoughts have gone in that intermediate time is I've seen a lot of soft failures. So it's great when it works, but if there is an intermediate network, either filtering ICMP messages or not 9K clean and filtering messages, that turned out to be pretty daunting to troubleshoot in practice. So it seemed to require some care and feeding, and you had to have some memory in the back of your mind that you knew exactly where you had turned that on, such that if they opened a support ticket, you kind of knew what you were getting into from this, that sort of perspective. And I want to say, I don't know if there's anyone from CERN on recently, that they just in the last couple of years had deployed a box that was screwing this up. So it's still a thing. You would think of all places that that shouldn't be occurring.
Yeah, I think I had a discussion with, you might know Eduardo at CERN. He was explaining the complexities of the network there and the many firewalls and ACLs that are applied in all sorts of places that do cause issues with the packet too big messages and all sorts of other. It's a complex network to manage, and I think that was part of his concern there, the complexity of the network that he was trying to enable to support jumbo frames.
Yeah, but it's great to see the test metrics and so on that you've presented here, Tim. That's really helpful.
Yeah, I see Raoul, my colleague, is on the call. So if anyone's got any questions about those tests, I'm sure he'd be happy to answer them. He has been running some more in the past week. So maybe if we take this forward and can agree a place to talk about it or a list to chat about it on, we can share and exchange more of those results.
Well, I'm excited to see Matt here, because if I learned anything, it all came from Matt. So even this documentation I have is probably a derivative work of your stuff.
I was looking at some of the dates in that web archive link you sent us, Matt. That's quite impressive.
I was going to say, as you're doing the talk, I wish I could add footnotes to all the slides, because I actually know the backstories for a lot of the things that you.
I thought you might. Feel free.
One thing I wanted to comment on is the reason it's 9K is it's actually so you could do page aligned buffers to make TCP direct sends work and have space for headers. It's actually 8K plus headers rather than 9K minus headers. And because in terms of optimizing the host, at least at one time, it was important you could do that. Now different architectures have changed and stuff like that. One of the things that I'm a little bit concerned about is you actually need to do some careful experiments on which MTUs are best. There's a corner case there used to be a corner case. And so part of the problem is I haven't done MTU for 14 years. I've stopped doing MTU about 14 years ago. But there's a corner case where an 8K buffer, page aligned 8K buffer gets a double page fault, and it's actually slower than a 4K buffer. And there's a bunch of stupid things like that happen, that it's not obvious why. You really need to not only do the benchmarks but understand why, because there's opportunities for really anomalous both false positive and false negative results. Well, false positive is kind of hard to define in this case, but the bigger thing, so I did RFC 4821, I think it was, right, the packetization layer path MTU discovery, because the ICMP host unreachable or MTU too small messages were not reliable. And we saw that it actually came about from that meeting at SDSC in 2001. It's like, we got to fix the internet to be resilient when the MTU mismatches cause black holes, because there's a bunch of court cases that you can't actually fix inside the network. And towards the end of that project, when the ink was mostly dry on the draft, at PSC, we had some beta test 10 gigabit gear that was sort of pre-release from Cisco. And we encountered a GBIC that ran error-free at 1500 bytes and 1% errors at, I don't remember if it was 4K or 9K. And this was a real shock. And I didn't fully comprehend what it meant, but I knew it was a problem for packetization layer MTU discovery because it would give a false pass on larger packets, this particular piece of gear. Thinking about it later, I realized, actually it was after I was already away from PSC, that the real problem with Jumbo is that it isn't standardized. And there's a reason it isn't standardized. It doesn't actually work very well. The problem is this: every piece of gear has two different MTU limits. There is a counter, which you can typically poke in software, but there's also a parametric limit, which has to do with the fact that at the end of the day, the network is really analog. It's like sending radio waves into the ether or something like that, and the sender and the receiver are not as tightly coupled as us digital people like to think. And in particular, let me give you a pathological example. 10 megabit Ethernet will easily go through the motions of 4K or 9K packets because it's a piece of copper. It doesn't care. But in classic coax Ethernet, the preamble is used for phase acquisition, and the clocking of the last bit of the packet is determined by the length of the packet and the frequency stability of the oscillators at the sender and the receiver. And what happens is that if you try it, if you test 10 megabit Ethernet at 9K, it'll sometimes work and it will sometimes not work. And what you've done is you've completely toasted the reliability requirements, the reliability specs, the noise margin specs, the bit error specs. And when you test it in the lab, maybe it works and maybe it doesn't work. And so you get sort of non-deterministic results. And it's a generalization across a huge space of designs, but this problem is pervasive in the sense that the engineers, the philosophical goal of Ethernet in particular is, if I buy a chip from China and buy a chip from Silicon Valley and plug them together, it will always work. And the problem is given that there's not a spec for what Jumbo means, excuse me, what you don't know is if you attain Jumbo by increasing the precision of the clocks, increasing the de-jittering buffer, doing ongoing phase correction. There's a whole bunch of different techniques that might be used. You don't know which of them are in play, and you don't know if a particular set of equipment has got compatible features. Inside of a data center, you can do the exercise rigorously. You can even look at the design. But the point where I wandered away from this was realizing that a real solution requires getting some inside help in the IEEE and trying to understand what would need to happen to make a Jumbo certification work. And it's sort of easy. I believe the answer in part is to increase the tolerance or increase the required precision for the sending clock, and perhaps a bunch of other changes at the receiver, and synchronous idle, which applies to all of the high-speed channels. You don't actually do clock acquisition on the preamble, and possibly explicit signaling at the MAC layer as to what the supported MTU is, or whether or not the supported devices do. And in absence of that, what happens is the lawyer engineers who write spec sheets and contracts won't actually, from the vendors, won't actually promise that Jumbo works. And at some organizations, they're banned from buying or depending on technology which isn't actually that the lawyers don't actually say is supported. And so there's this connect the dots in the legal space, which makes stuff that empirically often works but isn't guaranteed to work out of the scope for contracts. So it would be a huge step forward to independently start on what something that looks like a standard for it.
So two things. One is, how hard do you think it would be to develop a qualification test, right? So that you could at least say, chipset X does the right thing. I mean, so we saw this a couple of decades ago where IBM bought gig chipsets from a couple of different OEMs, and IBM branded them, right? They had two suppliers for redundancy and all those sorts of things. One of them, if you drove it flat out with jumbo frames, it would eat symbols. And it was exactly the preamble issue that you just described, right? The clock was off enough that the preamble wasn't enough to synchronize the sender and receiver for back-to-back packets at full MTU, right? So could we, because I don't think this is going to get standardized, right? I mean, I think the IEEE has basically said no. That's my understanding. So is there a test suite that we could use to qualify certain gear?
So that's the approach that I would take. What I had wished happened while I was at Google is I found an engineer who intimately knew Ethernet at the silicon level, who was inside the IEEE community, and there are such people at Google, but I did not know them. They were further than arm's length away from me, and to sort of start to think about what those kinds of things would need to be. I'm actually not very familiar with Ethernet. I believe all the high-speed Ethernets are synchronous. They use synchronous idle, and so there's not a clock reacquisition on a frame start, which is probably a requirement. And I don't know what other pieces would be the requirement. The plug and play requirement, which the IEEE believes in, requires that it be negotiated explicitly, not implicitly. Because you don't want it to be the case that if you plug jumbo certified into a non-jumbo certified, that you don't lie about being able to deliver 9K. And then the scary part is the false positives from doing a simplistic test. But I think the way to maybe get the IEEE to think about this is to do an outside effort to do something that looks like a certification test. And the goal should be that any pair of 10 gig certified devices would successfully and reliably deliver packets. One of the requirements that might be made is internet protocols, which the IEEE won't swallow, because you can require MTU discovery, you can require packetization layer MTU discovery, and B, that you're doing end-to-end error, end-to-end recovery. You're doing retransmissions. And with those three requirements, you can also do things like say, we don't need 10 to the minus 12 BER. We'll be happy with 10 to the minus 8. And the receiver spec that you want to change is relaxing the error rate required specs. And so there's a bunch of things that you might be able to do. I don't know how to do at scale things like thermal margin and voltage margin testing. I mean, I know how it's done theoretically, but I don't think any of us has the capability of doing it. But if you have a data center and the air conditioning's out one day, it's running hot, you don't want to discover that you can't talk to any of your peers because your clock drifted, and that kind of thing happens. Back in the fuzzball days with 56K kilobit backbone, one of the fun things that they could do is they could measure the temperatures of all the machine rooms by the clock drifts. So,
I suppose another way of looking at it is where we can find evidence of these sorts of problems, where we have systems that we believe we've configured to 9,000 MTU. I know you've explained why that might be a slightly naive view of it. and where there are higher or varying error rates or whatever the symptoms would be, how we detect what those symptoms are and understand that that might be what's happening, or whether
Right.
everything's actually okay.
And it may be that for a lot of devices, and I would expect if the receiver is, if it's a technology that's using a synchronous idle on the link, and the receiver is transferring data into solidified memory, which is true for a lot of devices. I don't know what span of devices, but small buffers that are chained together at high speed, that those devices may be completely tolerant to arbitrary MTUs in ways that other devices aren't. Another bunch of things to consider. The newer congestion controls, in particular, paste, BBR style paste sending is likely to have significant impacts on some of the performance results, and they could be in either sign. There is a corner case where I would expect 9K to actually perform worse than smaller packets. I don't know what the optimal packet size is. I have a hunch that the optimal packet size is actually whatever the host page size is. Don't know that, but I would guess that, and that requires optimization at a level that very, very few people can do to actually hit it.
Okay.
Well, so the other problem with that though is that, I mean, okay, so as you mentioned earlier, right, the original point of 9K was an 8K page plus headers, right?
Yeah.
If I remember correctly, that was an optimization for NFS, because NFS had 8K pages, if I remember correctly. But
that may be, PSC, for instance, has never run any NFS, so that wasn't in our thinking. So, but
okay.
yeah,
but
it may have been in other people's thinking.
So technology changes quickly, protocols change slowly.
Yeah.
And I think it is unlikely that we will successfully configure the internet to have the right packet size for the page size of a future computer architecture.
Right. So my goal in what I call jumbograms was that the internet supported diverse MPUs. It was not that it supported jumbo, it was that it supported diverse MPUs.
Right.
For exactly that reason.
Yeah.
But yeah, it was kind of a real flashback to see the announcement for this thing. It's like, man, I haven't thought about MTU. And I had on my to-do list, go find engineers inside of Google. I unexpectedly retired from Google in January. I'll put it that way. To find people at Google who both had a data center mindset and understand the value in jumbo and understood the silicon understood the Ethernet at the silicon level to actually understand what you would need to do in order to do a non-IEEE definite certification for jumbo and understand the politics around specific paragraphs in that certification. Where they cause the IEEE indigestion. And the number one thing there is that IEEE wants to be true that if I buy 2 chips from any vendors in the world, they say they're Ethernet, they will interoperate and they will meet the bit error rates in the spec. And the lawyer engineer will agree to that. Let them put that in contract language. And we're not there. And as long as we're not there, we're doing ad hoc certification.
So that sort of made me think of interesting, sort of recently in Ethernet, we're seeing forward error correction becoming more pervasive because these PHYs inherently cannot run without it. Would that be a factor that could help mitigate some of these issues? I can't remember in my mind where in the chain of events FEC happens versus where this clocking would need to occur, but something that came to my mind.
So if you look at one of the pages that's linked off of that page. Let me see if it's still there. The arguments page. Let me see. Well, I'll look at it. There was an arguments page, and in there was a calculation about bit error rates and such like that. And one of the things you realize that if the source of bit error rates is single flip bits, and you're delivering an object, you're delivering a terabyte of data, the total number of errors in that volume of data is constant, independent of how it's framed. And so in principle, if you go to larger frames, you can tolerate a higher error rate because you're covering more bits and so on. What I didn't realize at the time is that the encoding of the I've lost the word. The symbol encoding on the wire and the CRC are designed together such that the normal pattern for most single bit errors has to cause an odd number of bits wrong, and the CRC is deterministically rejects all packets with an odd number of bit errors up to a fairly long string of bits. And so it's not statistical. And you lose that property when the packet gets long enough for the CRC state wraps, because then it becomes ambiguous. You can't do error correction. And so there's some properties like that are pretty subtle that are designed into the CRCs for Ethernet and such. I don't know where that stuff is. I mean, I never fully comprehended all the subtleties of that stuff, but I did discover that the CRC that's used on Ethernet has a property that is provable, no false negatives for odd length bit errors, and that the lower layer is designed to only allow odd layers because it has to do with every symbol begins and ends with the opposite level. Something like that. I don't remember. Or every symbol. I don't remember. I don't remember the math anymore.
So maybe trying to ground it in practicality, what's your suggestion and advice at the moment then? There are clearly a number of sites who are running 9000 MTU, and the applications and use cases they have seem to work and give them more performance.
Right. So that's the issue. And it may be that you have inadvertently found a good enough ad hoc way of certifying it. As a practical matter, I mean, it'd be interesting to know what went wrong at CERN when they tried it and then turned it down.
I think that was the complexity of the network and configuring all the interfaces everywhere and where things are filtered or not filtered. Right. I don't think it was a specific issue with interfaces.
Yeah.
Well, I'd have to ask those people, but that was my impression when it was discussed in a HEPIX IPv6 working group meeting.
So one of the things that would help, for instance, is doing end-to-end error monitoring, TCP retransmit monitoring and stuff like that. And I do believe that some designs are truly jumbo safe, and some designs, some people say jumbo enabled if you can set the counter to 9K without actually thinking about whether or not they actually are reliable at 9K.
Yeah, we have seen in different tests, different levels of retransmits with 9K and 1500, but yeah, my detailed understanding of what's happening there is obviously not good enough to figure out why that is. But it is an observation you can make, that if you've just got everything else the same, sometimes 9000 gives you no retransmits where 1500 does, and vice versa.
Yeah. And I would expect, so the other thing to consider is the newer congestion control, which do paste sends with TSO, actually mitigates many of the things that jumbo fixes. And it may be the case that there are some environments where that's good enough. The congestion control, Reno and Cubic are hypersensitive to loss, and the TCP performance model is essentially about that story. And if your congestion control isn't actually using loss as a primary signal, then low-level loss doesn't affect it much.
So you say BBR, for example.
Yeah, pacing with small packets is actually much gentler on the queuing. And one of the downsides to 9K, which you haven't run into, is if you're trying to run a network really hot, the larger packets means you got to carve the buffer memory in the routers into bigger packets. If it's doing packet size buffers, the effective maximum queue depth is smaller. And if you're trying to run really hot, that's actually going to hurt you more than potentially hurts you more than the increase in the end system's performance, fewer interrupts and fewer processing. So it's a really complicated optimization. It's a global optimization across different domains, which is why I would consider carefully some experiments to see how much larger MTUs actually buy you on more modern congestion controls.
Yeah, so that everything that I showed there from Raoul and Richard was not using BBR, for example. They were using more traditional, for the want of another word, TCP.
So I do think 1500 is too small. I'll full stop say that. And the issue there is, if you imagine typical architectures with separated instruction and data spaces, 1500 bytes is small enough that there's a lot of protocol processing where you run out of instruction time before you run out of data. That is, the data pipeline ends up being blocked waiting for instructions. I believe that by 4K on most architectures, you can always get the protocol processing under a packet time for bulk transfers. And crossing that boundary actually makes a difference in a large number of environments. But once you've crossed that boundary, there's diminishing returns on bigger packets in terms of how much it saves you in the end system versus how much it costs you in silicon in the switch buffers, for instance.
It's an interesting point. Most of the testing that I've hunted out in the experimental results that you see are generally with 1500 and 9000, just like we presented here. You don't see much where they're saying, well, what about 4000 or other values? As you said, if you want a variable MTU, then you need to know.
At one point, we did some experiments. We did a bunch of different sizes that were close to 4K and 8K pages, and carefully page aligned and not page aligned. And that was when we discovered this anomalous result, that the double page fault on a 4K machine was actually more expensive than just sending 4K packets. So
I realize this is getting a little bit off of jumbo frames, but you touched on something that I've been thinking about for a while and don't have an easy way to test, me personally, which is, so you talked about the instruction time for protocol processing.
Yeah.
My hope for the new generation of AMD CPUs with much larger caches was that we might be able to get TCP into the L3 cache on the chip. And that might, help things a whole bunch. Now, it turns out that those are fragmented enough that maybe we can't do that. But I don't have the personal capability to explore that space in a way that I would consider reasonable. Has anyone done that?
So there are people at my previous employer that explore a different case, which is similar to that. And that is, what is the limiting number of YouTube videos you can serve off of a single server? And that turns out
Right, sure.
to be limited by the number of cache lines you need to hit in order to do protocol processing for one connection when each packet happens after you've completely flushed the cache.
Right, there you go.
Different part of the space.
Okay, but related, I would argue.
Right. It's a different side of the same coin. And it turns out in this case, the limiting capacity for many services is flushing the cache, doing GRO. that you basically can't make GRO work well enough. And GRO flushes the cache because you have to churn it. Can't make the cache big enough.
Okay, so I guess one of the things that I was sort of idly wondering is how might the TCP stack implementation be modified such that portions of it could reliably fit in cache, right?
Right. I know people have done that kind of work for single flows, and I actually thought that work was done a fairly long time ago, although it was probably the L2 cache, right? In fact, right, it's all old problems become new problems.
Sure. And well, and the other thing too is, if the answer is that it's too hard in the general case, then maybe that's not the right place to focus effort, right? And if that's the answer, that's okay too, right?
It's actually not that it's too hard in the general case. It's that the solution that you find often has a limited lifetime, because when they spin the chip, the answer changes slightly.
Nah.
And so you need to redo the experiment,
Right.
It's investing in something which ends up being silicon specific. And I have to say I'm jaded because I used to talk to people who actually understood how many cycles it took to do things in the chips. And it's amazing how fast you can do if you get this pesky operating system out of the way. And it's like, yeah, this is really wonderful. What are you going to do next year when they respin the chip?
I guess, again, coming back to the sort of practical side of things, I think at the moment, the NRENs, maybe many of them blissfully unaware of some of the issues you're raising here, which are obviously very important, are just trying to configure their networks to run 9000 MTU with whatever overhead they might need to make that work, regardless of, as I said, we've kind of done that largely, apart from one or two of our niche services.
Right.
But we're still only seeing a couple of sites using it. I mean, would you still be supportive of NRENs developing their networks with 9000 MTU in mind, regardless of the path by which we get there? Obviously, there is an amount of different types of testing to be done, but is that the advice you would give still?
Yeah, so I mean, it makes a huge difference in certain environments. I guess I would think about three things. One is keep whittling away at the barriers to path MTU discovery working, and dealing. The easy case is to make the ICMPs work. ICMPs don't work with heterogeneous MTUs on VLANs. The packetization layer MTU discovery was intended to fix that problem. I got a feeling it doesn't work anymore because that path isn't well tested, but it would greatly increase the robustness to not require ICMP to be able to do reasonably well at it. Our intent with that document was explicitly opportunistic jumbo discovery. Our fallback position to get it deployed was dealing with VPN headers, reducing the brittleness that happened from VPN headers in 1500 byte MTU. Very similar problem, but there's some key parts that are different.
So that probing option for V4 that YesNet's guidance recommends, and we've tried it and it seems to work. How does that actually work? I've not looked on the wire to see what it's doing. What is it? How is it actually doing?
So the trick is to take packet loss is to enable the stack to send a jumbo size frame, and treat the loss of the jumbo size frame not as congestion but as an MTU indication.
Right.
Okay, that's basically what it does, to make a long story short. And
so could there be an option like that for V6 as well?
It's done entirely inside of TCP, so it shouldn't matter. The issue is
Okay.
plumbing.
So the option just happens to have V4 in the name of the option, but okay, interesting.
You're talking about MSS? There's not a.
No, I've forgotten.
Are you looking like it in /proc, you mean in Linux? There's a number of knobs that are named IPv4 and are stuck there.
Yeah.
Oh, right. Okay.
Right. Yeah, they were misnamed. And like I said, the code path to use it for opportunistic jumbo discovery is not well tested. And every time somebody makes some fix elsewhere in the kernel to fix an NDU issue, they risk breaking that. And so I would not be surprised at all if it didn't work, if the opportunistic mode didn't work. But that was the original intent, is to support opportunistic MTU discovery. It also turned out that we didn't realize this until early on. That actually moves the problem down the stack, because the driver for the NIC doesn't have a way of asking the switch what the MTU is. And it broke the spirit of end-to-end opportunistic MTU to require that you configure the driver. But the problem with the driver can't use the same algorithm, because the first thing you do with the driver is typically some sort of buffer carving, which is expensive and can't be done once the chip is actually already started. And you're stuck with the buffer carving that you do. And if you carve the buffer into 9K packets and then find out you have to use 1500 bytes, you're wasting all that memory, which lowers the performance of the driver. And so you don't want to do that. And so it didn't work the way we wanted it to work. But if you still take the MTU from the interface, in principle, it could be used to do end-to-end MTU discovery. In principle, it could be used to do diverse MTUs on single LANs, stuff like that. It does cost extra time in those environments. It takes extra round trips because you toss packets and such. Yeah, I put a lot of time into MTU, into Jumbo. I put better part of it, I'll say part-time for better part of a decade. So.
Well, I always like to look optimistically at things as far as possible.
Yeah,
so I totally get what you're saying, and that there are things that need to be looked at in detail that are important.
Yeah.
But I think there's various things that could happen in parallel, and that's one. Right. I don't know here don't know who here is, for example, active in the IEEE community that might get involved with that, or whether there's existing something happening.
Yeah, it's pretty clear to me that the rank and file IEEE engineers are very much against it.
Interesting.
Yeah, and it has to do with they really want Ethernet to be universal plug and play. And if you defined a different class of Ethernet, a jumbo certified Ethernet, how do you potentially create a whole bunch of design rules that the IEEE has been successful at completely eliminating from Ethernet? There's not rules about spanning tree size, and there probably is for spanning tree, but not for a lot of other things. It just works. You plug it together and it works. But it would be, and then the testing that needs to be done on the ground is both sort of standard interoperability testing for the gear that you're purchasing, but then also imagining a test suite, where you do things like actually measure or document things like clock stability and stuff like that, clock accuracy. Like I said, I think the right answer is to tighten the sender's clock accuracy and then increase the receiver's tolerable error rates, and maybe a few other things, but those two are the big ones.
Coming back to the end-to-end testing, does one need to do checksums on the files at either end, or is the sort of packet errors going to sort of measuring those?
Let's see. There's an RFC which I was a co-author on, called. No, it was not about this per se. It was about not using fragmentation. By the way, you don't want to use fragmentation at all if you can avoid it. even though IPv4 supports functional fragmentation in the middle of the network, it does not support it at full performance. And it's almost certainly, you know, an abysmal path in the routers. If you look at the strength of the CRC and you imagine the kind of data set sizes people like CERN handle, the CRC is not strong enough. So the short answer is at modern data set sizes, you need to be doing yet another layer of checksums, object level checksums.
Right. So the LHC experiments, if I remember correctly, they use Adler 32, or at least they used to in their, I think it was just FTS used that, or it might be XRT, I forget which.
Yeah.
Globus uses MD5, which is lower performance, but stronger. And in fact, Globus failures were part of what pointed the community to a firmware bug in a particular widely deployed router platform about a decade ago that was silently corrupting packets. Right, it wasn't flipping bits, but it was shifting portions of the. Right, it was moving stuff around. So the arithmetic checksum still matched, haha. But MD5 some changed.
Yeah, and PSC ran into one too, probably more than 15 years ago. That was free before completely done with it type error that caused a buffer to be overwritten before the DMA was done. That was the same kind of symptoms. Scrambled data. It was, this one actually picked up on in SSH that the HMAC failed.
Right. I mean, this is one of the things, right? One of the limitations of arithmetic checksums, right? Statistical bit flips, sure, but if you shift or transpose on the wrong byte alignment, then it's completely transparent to the checksum.
Yeah. Yeah, there are a lot of war stories in this space.
Yeah, I mean, this comes back to, yeah, I mean, we discussed this topic in 3 or 4 other fora or working groups. None of them have come down to the detailed level that you've raised, which is, it's kind of refreshing and yet worrying in a way. I'm not sure quite how to feel, but I think it's important that all these perspectives are brought together. The interesting question though is from the war story point of view, when things aren't working, whether we understand fully the reasons that they're not. I mean, there are the PTBs being filtered is the whole PMTUD not working is one aspect. Another may be around for V4, the performance of the fragmentation or fragments being dropped, or as you say, all the other issues that go with fragmentation. So there's a whole, well, I say a whole bunch. There are a number of cases where sites are having a bad experience from trying jumbo frames, but how many of them are down to the sort of issues you've been raising today, it's not clear at all. It would be interesting to know.
Oh, just real clear, like when you see IPv4 fragmentation, its effect is so abysmal that you instantly know it, right? So from a troubleshooting perspective, when you went from gigabits to megabits, you know.
Yeah, definitely.
Yeah, that's why they took it out of IPv6. That although with software routers, it's not so bad. With routers doing everything in silicon, fragmentation just doesn't work. So
I'm not sure I ever heard the answer to what fraction of the ESNet network and the devices and so on are doing jumbo frames. Is it widespread or not at all, or everywhere, or somewhere in the middle?
Yeah, it's very specific to certain user communities. So one of the other uses of ESNet is supporting some of the bigger labs, and some of those run encryption services tunneled over ESNet. And I think those handoffs are at like 9100, so that they can put their jumbo frame inside the encrypted payload and then put that over ESNet.
Mm.
So, but again, that's like a really very specific use case, right? And then Eli, maybe you want to talk about like the LCF facilities.
Right. So the at least some of the big supercomputer centers run 9K on their DTN interfaces, and that's for the straightforward performance reasons that you would think of, right? Which is getting the packet rate down, and getting and reducing the number of round trips for congestion loss recovery, right?
Yeah.
But then the some of the big LHC sites have flatly refused, right? I mean, as far as I'm aware, Fermilab will never deploy jumbo frames, and at least part of it is some of what Matt was talking about earlier, right? Which is they don't want to overdrive the Ethernet checksum. But I think, you know, it might also just be that they don't want the complexity of dealing with working on troubleshooting something that amounts to a misconfiguration that somebody else did, right? Because that's, you know, you find yourself doing that a lot in troubleshooting MTU issues, right? You know, your stuff's configured correctly, someone else's isn't configured correctly, but what it means is I now have a support problem because one of my users can't get their work done. And so there are some sites that have been unwilling to take that on as well. And so, you know, as Dale says, right, it really depends which, you know, what your focus is, why you're doing whatever it is you're doing, and so on. The other thing too is that, like, if you look at the LHC experiments, the per flow data rate requirement for the LHC experiments is actually drastically lower than it is for a supercomputer center, right? Because they have a gajillion file transfers that are sort of hundreds to, you know, they're sub gigabit class flows, right? And they've just got a gajillion of them sprayed across tens to hundreds of nodes, right? So in aggregate, that's like really big. But in terms of, you know, do you need, you know, a network layer optimization that gets the packet rate down in order for that to work correctly? No, actually, you don't.
Yeah.
Right. Whereas if you're a supercomputer center and you're moving petascale data sets over a relatively small number of TCP connections, right, the math is different.
Yep. Exactly.
Yeah, I think there's quite a misconception. We saw an example, Dan and I, on a list today where there's discussion about the packet marking, that people just assume the WLCG stuff is a small number of very large flows, but actually it's anything but generally.
Yeah, it's not. Right. And so, you know, for a network, right? So for us, you know, and, you know, for JISC as well, right? We have to support all of them in the general case. Right.
Yeah.
And so, you know, it changes one's outlook a bit.
Well, I think as a NREN, you know, what we should be doing is ensuring that we support the ability of our connected sites to use 9000 MTU in the lands if they wish to do so. Consenting sites wish to do it between each other, that's fine, and we shouldn't do anything that precludes that.
Exactly.
Same with various other services.
So that's not a free lunch either these days. So
No.
in the era of, I would say, like 20 years in WAN transport with MPLS encapsulated networks running RSVP or LDP, you would slap on 1 or 2 MPLS labels. So maybe you're adding on 40 bytes, maybe a little bit more, depending on how crazy you're putting tunnels inside the RSVP tunnels. With segment routing, I am now worried about further numbers of MPLS labels putting on, and we're pushing up very closely to the edge, if not exceeding the layer 2 MTUs of many platforms, which is usually around 9200, give or take. So you've seen, like, you'll see like a 9172 to like 9018 range, right?
Interesting.
So start doing the math of, okay, you want a 9K payload, you're going to put Ethernet header on it. Now you're going to stamp on how many MPLS labels. So of L3 VPN identifier, you might have for segment routing your egress node SID, if you have any other intermediate node SIDs for traffic engineering, if you're doing TILFA traffic restoration, that's 1, potentially 2 more labels when there's a fault. So you would never know that there was a problem unless there wasn't a link down. It tried to put on the extra label and your traffic can't get there. So that's sort of where my headspace has been recently. It's like, wait a minute, we need to really think about these encapsulations.
Well, the whole segment routing topic would be a nice one for a
Well, don't
seminar
get me
series
started on
like this.
SRv6. This is just, you know, real people see this segment routing.
Yeah.
Yeah, this is why I would try and pull back and go with an 8K MSS rather than a 9K MTU. I was just thinking I don't actually know what the kernel supports anymore.
Yeah,
Sorry, go with what, Matt, instead of a 9K MTU?
8K MSS, maximum segment size,
Right.
which is TCP's payload, rather than
right.
9K.
So from a protocol perspective, I mean, none of the protocols support those semantics, though. Right. I mean, that'd be a fair amount of work. I'm saying it's not the right thing, right? But it, you know, just in thinking about it, it's like, okay, that's going to be hard.
There might actually be a knob to limit MSS independent of limiting MTU, but I don't know.
You also sometimes see it on middle boxes, referred to as
That would
like
be cool.
MSS clamping.
So if we
Yes,
could do
MSS
that would be great.
I know some firewall platforms, well, granted, they're firewall
Lots of middle boxes
Do
that
that.
are doing clear text rewriting put in MSS clamping
at line rate.
at line rate. Yeah. Well, you only have to do it on the SYN. And you don't even need to do both the SYN and the SYNAC because each side affects only one direction.
But if we're doing performance testing of this, the obvious thing from what you've said, the obvious thing is to test at 4K plus the TCP headers, 8K plus the TCP headers, and then the full 9,000 MTU packet size. Are those a reasonable set of numbers?
That sounds like a good plan.
And also test file corrupt if we got the ability to check file corruption, and then that again is see how that changes if it does change.
The file corruption checks ought to be built into the applications. They should always be there if you're doing petabytes of data.
Yeah, they are. Whether in changing the MTU we get access to that, it sounds like it would be useful to work out whether the file corruption does go up. So that's that's worth thinking about. Thank you.
So I think in summary, I feel much better informed than I was 85 minutes ago. Whether I'm happier or sadder, I'm not sure. Yeah, well, I mean, what you suggest, Chris, sounds good. I think we should be doing tests that try and confirm or deny some of the points that I think you made right at the start, Matt, about weird behavior for smaller and larger MTUs and being contradictory, etc.
Just being aware that
makes sense.
That there's a parametric failure mode that you always have.
But in the meantime, still trying to support what Dale said, 9,000 MTU, and maybe doing some tests to see which NRENs support that capability and how much headroom they've got. You could probably test in ways to figure that out.
We do run a lot of tests, don't we? And if you think that some of the largest CMS sites and Atlas sites in the US are running on 9,000, and they transfer data to sites like Imperial College in the UK or many others on 1,500, and we don't see errors.
It just works, yeah. But
just works.
So I think the thing with the WLCG is they have,
tests.
and maybe people here are aware of it, there's the Data Challenge 2024, which is happening early next year. And they have mentioned in the DOMA working group, I think, are doing the sort of planning of this. They have mentioned that they want to be looking at jumbo frames as part of that. So I think some of the things that have been raised here should be flagged to them in terms of the testing and what they're doing to help inform them. I think it's understandable that they would want to test jumbo frames, given that the volumes of data they're going to be moving are going to get much bigger. However many individual network flows that boils down to, Eli, it's, you know, they're talking the high luminosity stuff of some significant growth in the volume of data they're moving around. I think next year, the data challenge, they're looking to do about 25% for high luminosity. And that's still, I think the dates have gone back, that's still like 28, 29, that's coming, but it'll come here quite quickly. And there's going to be 400 gig line cards or more in place at those times. Yeah.
All right. Well, it sounds like we may be hitting a stopping point here, unless anybody has anything else they'd like to bring up.
I have a footnote. There is
Sure.
a kernel parameter, which is TCP base MSS. And if you set that, you can essentially bypass, you can set it, for instance, to 8K, and it will not do full-size packets on a 9K network. TCP, syscontrol TCP base MSS.
And it looks like IPv4 might pass that through. Also, I'm guessing that it might show up as a set sock opt.
Yep.
Yeah, we should try and find something happy to end on, because there's a lot of questions that have been raised there. So I think we should be optimistic. I think we should try and push forward with ensuring capabilities there, but to do meaningful tests and to understand what the meaningful tests to do are in the way that you were talking about earlier, Matt, not just like, okay, some of the tests I was showing, they're somewhat naive in a way,
Yeah,
that they're just the 9,000 and 1,500, and there's more than that that we should be doing, is one of the takeaways for me from this.
Right, and this option would let you easily do the experiments where you check a range of sizes and discover that 8K plus 2 bytes really sucks, for instance.
Right. So I mean, the test harness that Brian developed to do the big round of BBRv2 testing that we did a couple of years ago is actually really helpful for this sort of thing, because it allows you to easily do parameter sweeps across persona hosts, right? So you don't have to like do all of that stuff manually and keep track of it all, right? We have a framework for that, and so this. Brian's doing some stuff for us this year, so I'm going to pass this along to him and see if we can play with that a bit.
Sounds good.
And Brian actually sent me a text during the call and says he's looking forward to hearing this recording. He is sorry he could not be there live.
You better warn him it's longer than the usual recordings.
He's retired. He's got plenty of time on his hands.
Bumper episode.
Going forward, we fully expect him to join from his camper van.
True. All right.
Anyway,
well,
thank you very much for the invite, Jason. And yeah, I think it's been I've learned a lot from the discussion that I haven't learned in 3 or 4 other discussions of jumbo frames in other communities. So that's been really useful.
Yeah, thank you for the invite as well. Although, it was.
Yep.
It was
and certainly don't be a stranger, Matt. You know, you're always welcome to come in and bestow some wisdom on all of us.
I can't keep that reputation up forever, though.
All right. Well, I hope everybody has a good weekend. We'll get the slides posted and the video posted, and we'll talk to everybody soon.
Thank you.
Right. Thank you very much, everybody. Bye.